discounts on conferences. So I personally, I read the magazine a lot. Look at the papers online. Transactions is free, things like that. So these are just a short list of the publications. And then there's lots of ways to get, more involved in the society based on your interest. So like, myself, Stefan and Ted are very involved in the Connecticut chapter. But there's, more technical track ways to go through different programs and projects, getting involved in standards, publications, technical activities, and then more on the people focused side, like chapters, membership. If you're passionate about getting young professionals or women in engineering involved, there's ways to do that. I like to say there's kind of a home for everybody. And so it's like a lot of things. It's you kind of get out what you put into it. So you can kind of get involved in these different ways. Pick a topic, get involved in meetings like this one, conferences, webinars. You can volunteer and then make contacts, and it's a great way to keep up to date on latest technologies and research. So that was about quick intro to the top level organization. So our vision statement as a chapter, we're relatively new, like about 2 years old now. So our goal is to be the go-to organization for Connecticut power electronics professionals for knowledge sharing, networking, and mentorship by kind of providing a bridge between industry and academia. So I'm an industry person, so that's where my background and allegiance is a little bit, but we work closely with, UConn, CCSU, the different colleges in Connecticut, as well as, try and engage with different companies around the state. So these are some, like a quick overview of our past activities. So in the past year or so, we had some good webinars. Each December we have a social event. So be on the lookout for that, as well as I didn't include it in this one, but anyway, so earlier this year in April, we had an event with UConn and Yale Formula SAE. So that was really cool. The students kind of talked about their cars and things like that. So they gave some of their lessons learned and things like that, and we kind of talked with them. So that was a fun event that we hope to do again. So next week, Stefan and I will be involved in the ECCE. So our chapter is kind of sponsoring a panel that some engineers from Connecticut and New Jersey will be in. And then about a month from now, November 14th and 15th, it is, right, is the second annual Northeast Power Electronics Symposium. So I'll make sure everybody gets the information about that. But that'll be at UConn again. So it's a full slate of activities for 2 days. So it should be good. Some good activities planned there with UConn and their Power Electronics Center of Excellence. If you're interested in a PELS code, unfortunately, it's only good for the less expensive the PELS part. But anyway, if you're an IEEE member, you can add on the PELS membership for free. So here's our XCOM. And so I would like to thank in particular, Stefan, for all your hard work putting together tonight's event. So thank you. Thank you very much. So you can feel free to reach out to me if you're interested in getting involved. So I think I did okay on time getting through my boring piece. So now I would like to introduce our speaker, Dr. George Gela. So he's an internationally recognized electric utility expert with a PhD in electrical engineering and an extensive background in research, testing, and teaching. After graduating with his PhD from the University of Toronto in Canada, George joined the research department of Trench Electric, manufacturers of high voltage air core reactors. He taught graduate and undergraduate courses in power systems, power electronics, and renewable energy at The Ohio State University in Columbus, Ohio, and the Western New England University in Springfield, Mass, and RPI in New York. So he's an active member in IEEE, ASTM, ANSI, ICOLM, the Live Working Association in Europe, and served for 21 years as chair of IEC TC 78. Um, so you have certainly a lot of extensive background and expertise in the area of power systems, and we're very fortunate to have you here tonight to give a presentation. So with that, I would like to turn it over to you, Dr. Gela, and thank you again.
Okay, thank you. Okay, I was muted. I will very quickly repeat. I've been with IEEE since 1950, 1983, I think. And this presentation on manhole events, manhole problems or explosions, is really not related with power engineering or power electronic society. It's explosions in manholes, underground cable systems, and it's not starting. Okay. I will try. No, not this one. This one. I will try to start this one. I'm not sure which one it is. No, not this one. This one. Okay. And events. Lots of. There it is. I think it's this guy. Okay. So I will. No, it's not even this one. I'm not sure where it is now.
Is it a long video?
It's a very long video. We're not going to play the whole thing, but I'm trying to find it. I'm trying to find. Oh, there it is. Okay. And those are raw videos that I downloaded this one from the internet. So it's sometimes it takes a while to start and load. Well, it's not working for some reason. Open. It's only 488 megabytes of memory, so it takes a while. If I can't start it, I'll try something else.
You click in the bottom right, is it?
Stop share, no. It's supposed to, but I always had problems with it because these are raw, unedited videos, and sometimes it just doesn't start. Okay, so let me back up a little bit. Manhole events, so we call them, are violent explosions of underground facilities, and there are cables. Sometimes sewers are also active. It may not load for whatever reason. If it doesn't, I'll try something else. Okay, so you have underground facilities, underground cables, electric cables, and okay, let me try some. Let me try the presentation. I'll talk about the presentation. Where is it? Not videos, but the presentation slides. Okay. Manhole events. What is a manhole event? Explosion cover is launched, and on the right-hand side, let me try to delete this somehow. No.
Click X.
I'm trying to click on it, X, and it's not.
Do
Leave meeting.
no, don't do that one. Do minimize.
This,
No, little right. Little right.
this.
Yeah, that one.
Okay, no,
Then click this one.
this.
You want to get rid of this thing?
Yeah, I want to get rid of
Yeah,
all
here.
three.
I can.
Okay, because it's covering the.
Yeah.
Okay.
And then if we want to
Okay.
go full
That's good.
screen, it should hide
Full
it.
screen. Yeah. I grew up on an IBM 365, so this is also new to me. Okay, it's an explosion. The cover is launched. What explodes are gases, and then we'll talk about where those gases come from and what types of gases. What is the source of ignition? Well, very often it's some sparking between cables. Insulation is deteriorated or by, I don't know, by rats. They chew on cables, or by cables rubbing on each other. The insulation is damaged, and you have a spark. The spark can ignite gases. When cables overheat, they release gases, and we'll define those gases later on. Why sparking? Because there's some damage somewhere. Why is the cover dislodged? Because the gases expand, and during the explosion, there's rapid, great expansion, and the cover is launched. Something has to give. Something has to allow the gases to escape, and so the cover is launched. How do we then prevent both the explosion and the cover being launched? Preventing the explosion is much more difficult, but restraining the cover from leaving the opening is a little bit easier. And that's what we did, what I did at EPRI starting in 1994. So it's been about 20 years. I left EPRI in 1914, sorry, 2014. So that's been about 20 years. And the research and testing is continuing. Okay. I think we defined the main parameters, main reasons, and main ways to prevent the explosions or preventing the covers from being launched, but we're not done yet. Okay. Collateral damage can be, well, here's an example. The lower picture here is, I don't have a pointer. The lower picture here, the cover was launched and flipped the car on its side. Fortunately, there were no serious events where people were actually injured. There is a video online showing a mother pushing a baby carriage, and just as after she crosses a certain point on the sidewalk explodes. So, very scary event, but no injuries at that time. in that event. Okay, let's go to the next one. How do we contain restrain the covers during the explosions? Okay, here is the same picture again at the top, on the top left-hand corner. Lots of newspaper stories and all kinds of articles. And the middle picture shows the facility at EPRI that was built, and the cover is actually launched here. The cover is launched. Okay, so you can see that it does actually. The cover weighs about between 20 and 300 pounds. So it is launched. Okay. Historical overview. I went over that very quickly, and this is a view of a cover on a pallet. It's not installed anywhere. It's a cover on a pallet, just to show you the size of 32 inches in diameter, or 40 or 46 inches, something like that. Large enough for a person to climb down the ladder into the manhole to do some work. Okay, this is a picture of a manhole with a certain design scoped underneath to allow gases to escape under control conditions. Okay, so this is an example of Swivelock. Swivelock is a company somewhere in Detroit that tried to find designs, cover designs that would restrain the cover from being launched and also release gases. Okay. Is further research needed? Yes, definitely. Okay. Okay. Gases related are rare events, explosion rare events, but they do happen. Here is another picture in the upper right-hand corner of the facility in EPRI, Lenox, Massachusetts, just south of Pittsfield, during an event, deliberately setting off an explosion. Okay, here is the lower picture shows the underground underside design of a cover with a restraining system, which works to some extent. Okay, major gas-related manhole explosions are rare, but there are 250,000 structures in Northeast, about 2,500 events, and about 25 dislodged covers over the past maybe 10 years or so. Okay, so most of the events are not very destructive and not even noticeable sometimes because the cover ends up in its frame. But there are very serious covers that could cause serious injury. Most of the non-explosive events are called smokers. There's gas ignition, and it sort of smokes out, exits, escapes through the hose in the cover, and that's it. Now, the covers do have hose, at least 2 hose, because the worker has to remove the cover somehow, and usually they use a steel hook. Okay, so the covers are not deliberately designed to be vented or to vent or in the past they were not, but they do have holes. Okay, so we have about many more smokers than actual dislodgements. Okay, just to give you an idea of the severity. Venting, restraining, tethers, controlled are ways to try that many, not only we, but many manufacturers and utilities try to prevent the dislodgement of the cover. Okay. Venting is not very effective. Controlled pressure relief is effective. Okay. Effective, not in all cases, but designing the cover to relieve the pressure in a controlled way is not an easy task. Okay. Here's a summary. Here's another example of that car being flipped, and that's not the only picture that we have. Here's an event where the cover was actually dislodged. No injuries, no flipped covers, but the flame burning gas escapes to quite a height. Okay. Okay. 1991, Duquesne Power had a fatal event that was not a gas explosion, but the cover was dislodged for other reasons, and it caused a fatality. 1995, okay, one step back. I talked about gases exploding, uncontrolled explosions. What kind of gases? What's involved? Okay, well, EPRI sponsored a project at UL in Chicago, just outside of Chicago, to determine the composition of gases evolving from overheating cables. And UL took many cables, overheated them in a controlled environment, and captured the gases and identified the gases. And the gases are very friendly. Hydrogen, carbon monoxide, methane, ethylene, and acetylene. Okay? Hydrogen obviously is very light. The other four gases are quite heavy. Then EPRI came to the Lennox facility, and it was just a coincidence that I was sitting next to the EPRI manager for this project in 1990, actually in 1993, 1994, and he asked whether it would be possible to build a facility to test the covers using those gases. I said, of course. I know nothing about gases. I know nothing about explosions. I'm a high voltage engineer, but why should I say no? Okay, so we built a facility. And here is the historical run through. Swivelec is a company for the first company that tried to design and develop a cover that would be dislodged in a controlled way and relieve pressure in a controlled way. Okay, so we built a facility in Lennox, test facility, which consisted of underground structure, one large manhole with an opening and a cover. Another one smaller facility, and the third one also somewhere in between, and three service boxes, and small boxes, which usually use graded covers, not round rectangular covers or square covers. Okay, here is an example of three covers that were tested. This is steel or iron cover with many large holes. This is one in the middle, bottom picture, with many small holes. And here is a plastic cover on the left. The question was, which one is better? Okay. I'm not going to go through this text here because that's not very details that we will address later on. Okay. Gas, methane, ethylene, acetylene, and carbon monoxide. Those gases approximately have approximately the same specific gravity. Hydrogen, of course, is very light. So the decision was made to test events using only hydrogen, and also events with these four gases: methane, ethylene, acetylene, carbon monoxide. This is an example of one of the first tests with the cover removed, and we had an igniter in the manhole. You cannot see the manhole. You can maybe see the black area here in this picture at the top. That is the top of the facility. And we ignited it, and that's what we saw. Gas ignited, gas rising. Nothing surprising about that, but nobody has ever seen this. Okay, and here's a shed that contains all those gases, piping, and so on, and control desk. Okay. Overview, if you have been to the Lennox facility, it's south of Pittsfield. in a rural area. There is one neighbor to the right of this facility in this picture. It's not in the picture, actually. So we could do all kinds of things with very noisy, and there was nobody close to complain. Okay, so the ideal location. The manhole facility is in the upper right-hand corner in the red circle. The rest of the facility is a high voltage laboratory, outdoor laboratory. Okay, and the first design of the facility was built in 1994, designed in 93, built in 1994, and it represents a one block in Manhattan. Why Manhattan? Because Manhattan is close to Lenox, relatively close, and they did have several events, and they actually funded the part of the facility, building the facility. Okay, and you can't really see that in this picture, but it consists of one manhole, large manhole, a smaller manhole there, a smaller manhole in the lower right-hand corner, and 3 service boxes, all interconnected with 6 conduits, steel, galvanized steel, black iron, plastic, and some other, which I don't remember. Okay, and they are all interconnected. We also wanted to study the propagation of either the flame front or the gases through these pipes from one facility, from one area to the other. Okay, 2 manholes, 1 vault. Okay, the large one is called a vault. Here is the diagram. This is M11. It's a manhole 11 feet long inside length. This is 14, so it is actually larger, 14 feet long. This is a vault which may contain transformers. It did not for our purposes, but it's a different design. The connections are on the sides of the facility of that structure, whereas on M11 on the ends. And service boxes, larger and smaller service boxes. This one is actually bypassed, but by some of the pipes. So a very flexible combination of paths for the events. Okay. Various types of conduit. Gas injection system was close to this M11, and we had acetylene. We have the acetylene bottles. You have to be careful with acetylene bottles, because if you remove acetylene from the bottle at a very high rate, it will decompose. So we had to design the injection rates for all the gases, making sure that the injection rate for acetylene is not excessive. So the injection time, depending on how much gas we wanted to have in the facility, in the underground facility, sometimes it would take 4 hours to inject. So it would take maybe 2 tests per day, maybe 1 only, because we had to inject for maybe 4 hours, perform the test, make sure that nobody is around. And in one case, I almost stopped the test ignition about 5 seconds before ignition, because I could not find one of the guests, and he was sitting in a truck close to M11 and would not respond to. Okay, so it was my responsibility to make sure that everybody is safe, and I almost stopped the test. I just pulled them out of the truck and got them out of the way. Okay, so sometimes it takes about 4 hours to inject gases, which means that and then preparation, ignition takes not long, but after ignition we have to vent the whole system. That takes some time. So we may we may do 2 tests per day or only 1. So it is very, very important to make sure that everything is fine and ready to ignite. And the igniter was a spark plug. Okay, it doesn't take much to ignite gases. Dacron netting around each of the locations, M11, M12, Dacron netting shown in the upper center picture, and 2 layers of Dacron netting to capture the cover, because first we didn't know how far it will fly. So we designed this tent to capture the cover, and in one case, we're not sure whether the column of flame melted the Dacron or whether the cover actually punctured it, but the cover ended up outside the tent. Okay, nobody was around because that was my responsibility. Okay, since then, just before I left EPRI, there was another adjacent facility built, very large, like a transformer underground, the vault, and it was tested as well. Okay, here is an example. Here is a sketch of the M11 manhole. On the wall, on the upper right-hand corner, here is a sensor. We had sensors, we had pressure sensors, temperature sensors, and the igniter. Okay, and inside a camera, high-speed camera and a low-speed camera, and an outside high-speed camera, low-speed camera. Okay. We had to calibrate the internal and external pressure and temperature sensors, and adjust gas bottle regulators, and so on. So it's a long procedure. So research took several years, almost 20 years, but we did not perform tests every day because we needed to secure funding for each one. Okay. And also then we tested non-round covers, rectangular covers. Now somebody came up with a brilliant idea of a cover with not a hose, but like a tent, like a fence. Okay, and guess what? Didn't make any difference. Oh, didn't make any difference. It would still dislodge the cover. This one on the lower left-hand corner, this is a rectangular cover. One is steel, another one is plastic. So the shape of the number and the shape of the vents really was not a very important factor. Once the pressure builds up, gases explode, the cover flies. Okay, that was one very somewhat surprising, but also very important finding. Okay, pressure inside the manhole and around the cover's trajectory, we measured that from high-speed cameras, using high-speed cameras. Temperature, we measured that. Here is an example of the exhaust gases, the frames from a high-speed camera. Here is on the CH1, that is the location of a temperature sensor. The lower right-hand corner, the entire roof slab was dislodged. Okay, so events can be very, very violent. Okay, I do not remember the concentration of gases in this very violent case. It was something like 10% by volume of a mixture of gases, not necessarily 10% of acetylene, 10% of carbon monoxide, but the total gas accumulation was total 10% of the volume, which is unusual, but we needed to go that high to determine what would happen. That's research. Usually in research, you go to destruction, and we did. Here are frames from a high-speed camera, inside view, upper row, and outside view, lower row pictures. Here is the moment of ignition. That's 0.01 seconds after ignition was applied. There is a little flame. Then it grows. Then it grows. And finally it fills the entire volume. And at that time, the cover starts lifting. And the first hundredths of a second, the pressure starts building up for about 0.12 seconds, 0.16 seconds. Finally, the sphere of ignited gases reaches the cover, and that's when the cover starts feeling it and starts lifting. Okay, and you can see the cover is gone. Okay, the previous picture was at 0.2 seconds. At 0.24 seconds, the cover is gone already, because the pressure has built up and lifted the cover, dislodged the cover. And for the rest of the movie, I took only frames. I found these things on the internet, actually. If you look hard enough, you can find them. And this one, 0.48 seconds after ignition, nothing. The cover is somewhere, probably hitting the roof by now, roof of that tent, but the flame is gone. The temperature still can be quite high in this area, but the event is over. Now you have to worry about where the cover will land. In one case, and that was a miscalculation on my part, we supplied too much acetylene. I had a spreadsheet, okay, calculating the number of minutes during which we need to inject gases. And it took about 4 to 5 hours to inject the required amount of acetylene, because we have to withdraw it from the bottle at a low rate. So I said, well, let's double the acetylene lines, twice as many hoses, twice as many bottles, and cut the injection time in half. So I prepared a spreadsheet. I got 2 other engineers to check my calculations, and they agreed that everything is fine. After the event, we found that I forgot to divide something by 2. We found the cover about 125 feet in the farmer's field. It reached probably 100 feet, height of 100 feet, and the entire roof slab, concrete roof slab lifted. That was shown in another picture. Okay, accidents happen. Okay, once we went through that experience, we knew what to expect. Now we asked various scientists to design restraining systems. Okay, well, one is or mitigation systems. One is to fill in the volume with an injected with a plastic balloon. Okay, and that would reduce the volume of gas, reduce the concentration of gas of the gases in the manhole. Well, what we found is that this plastic would immediately melt. So it didn't help. Then there was a very strong, heavy steel restraining system, a bar underneath to restrain the upper right-hand corner. This would slip over a pin mounted on the cover itself and locked in to prevent that from dislodging. Well, the cover did not dislodge, but damaged inside. Okay, and damaged some other items of the setup. A steel cable didn't help. The cover would lift to about 2 feet. Then the question arose: how high should we allow the cover to lift? Any ideas?
5 inches.
What?
So then if the car is driving over.
That's exactly right. Yeah. I scratched my head for a few days, talked with other people, and finally we looked at our cars. And the muffler is about 5 inches of 5-6 inches above road surface. Okay, so if we want to vent the gases without flipping a car, then that's the height that we can allow them to rise. Okay, these systems would not work. We have found out the hard way. We did not flip a car, but we just measured the height. Okay, something like this, a plate that would prevent the cover, that would redirect the gases, okay, and some other direction, and maybe prevent the gases from escaping. Well, okay, we had some doubts about this, but we tested it, and what we found is that this steel plate, which was suspended from the frame, would just be pushed into the frame and block the entire cover frame. So the gases had no place to escape and would rip the whole thing apart. Okay. In one case, the cover entire roof slab, reinforced roof slab, provided by a utility from everything was real. It was not just imagined or simulated. 1,300 pounds lifted. Okay. Okay. These things with simple cable restraining the cover would flip if it's only one cable. If two cables, it probably would rip the cable. And then the question was, okay, fine, but how do you remove the cover with that thing attached at both ends to some sort of anchor in the manhole and anchoring the cover? So this was both impractical and would not really solve the problem. Okay, and then we tried what really worked to some extent, to the best way. I don't think that we have the complete solution, but a hook attached to the cover and a pin that would shear if the gases if the pressure is still very, very high. Okay, and we tried different pins and so on, and finally, I think now, and I've been out of the area for 11 years now, but now I think they are much closer to a solution, not in necessarily large volts, but in smaller volts, which are much more common for smaller handholds that are much more common in the area and in the cities. Like, you don't have very many transformer volts with maybe two covers or very large volume, but there are many smaller handholds that contain maybe connections, maybe smaller devices. Okay, and those can explode as well. Okay, this is a picture of the largest manhole that was built just before I left, and the Swivelock company out of Detroit tested a number of designs and finally came up with a relatively reliable system with a shear pin, which would allow the cover to rise, but not very high, not more than 5 inches. Okay. And more pictures. And this is an example of the entire roof being lifted. So you do have to relieve the pressure somehow in a controlled way. This is an example in the upper right-hand corner. You can see this whitish smoke coming out. That cover has a restraining system, but allows the cover to rise to vent the pressure. So that is beginning or was beginning to work at that time. Okay, then we measure the height, we measure the pressure, we measure the trajectory of the cover, and this is quite high. This is about 12 feet. Okay, and how do you measure that the height without stepping too close to the area? We had to evacuate the area to a perimeter of about 50 feet around. Okay. Some examples of other events in various cities, not only Boston and New York, but things like mitigation methods really don't work. Empty ducts, what we found is that the pressure is increases so quickly that the ducts connecting that manhole to other locations just simply plug up. Okay. The pressure does not propagate. So even and usually those ducts in an installation are filled with cables, but even removing those cables would not help. We also looked at moisture or water ingress into a manhole, and because that could accelerate deterioration of insulation of cables and so on. So a lot of other questions were addressed. Proactive approach. We tried to. Well, I was not involved in that. That's public relations. It was not my area. But the media always ask, "What are you doing to fix this?" We tried to answer the question of what fix means. What do you do to fix it? How can it be fixed? And media took that and interpreted it as either not doing anything or they're trying and not succeeding. Okay. Then research results versus implementation. That's another major step. Whenever you're developing something new and try to implement it in the real world, it's not going to work the same way. Okay. I was invited to several countries. One was China because they had events as well, to explain what Apple is doing, explain the events. I was invited to Venezuela, to Brazil, because they had their own problems, and not many in Europe. Not many events in Europe, which was interesting to find. Okay.
Is there any reason why not in Europe?
I am not sure. There were many reasons stated, but I'm not sure whether they are legitimate or not. I was told many stories. Maybe the insulation is better, cable insulation, or thicker. Don't know. Or maybe they restrain the cables and cables don't vibrate and rub against each other, because that can happen due to heavy traffic. I left that a long time ago. I'm not sure. Okay, and a road surface, the thickness is much higher in Europe, larger in Europe than here. Okay, so that could be a reason, but maybe somebody is investigating that, maybe not. I don't know. Okay. Okay, here is another one. Long-term manhole research, improved cable material. So yes, that's going in the direction you're saying. Early warning signs. I'm not sure how effective that would be because there's not much time between the ignition and the explosion. But if you can monitor the environment in every single service box and every single manhole, you will find that it's very expensive, costly, because somehow you have to record the temperature, pressure, and buildup of pressure, send that signal to somewhere, and then what do you do with it? Okay. Mathematical modeling, there is an IEEE standard on this. Okay, I don't remember. I have it later on, but there is a mathematical standard. The IEEE standard that summarizes all these things and also shows calculations that match reasonably well that is experimental data. This is a record of pressure buildup. Okay, so the measurements actually match that to a good extent. Okay. Okay. Revisiting the UL report. The UL report, remember I mentioned that UL defined the mixture, typical mixture in a manhole, mixture of gases. Now, that's not always true for every single situation. Okay, so computational methods allowed variation of concentration of gases or amount of gas and come up with some sort of guidelines. Proportion of H2 in the mixture is also very important because hydrogen is very light. It would settle close to the top of the manhole and burn very quickly. Okay, so that was not included on most of the tests because just two totally different timelines of the event. Okay, some statistics, and I think I went through that already. Many events at Con-Ed, BC Hydro in Canada, Detroit Edison, San Diego Gas and Electric, majority, more than 95% of data from Con Edison. Why? We don't know. Maybe because the infrastructure is very old. Okay. Maybe what they also found, not that's part of this investigation, but another investigation, that there are many stray currents in the structures, in the manholes. And a lady was actually killed by falling with one part of her body on this manhole and the other on the sidewalk steel sidewalk. Okay, difference in potential current, or actually current through her body. So that was unfortunate, but that could be another important factor that should be considered. Right now, I don't think there is much activity at any facility anywhere around the world because some answers have been provided and we don't hear about explosions. Okay, one way to attack the problem or prevent the problem or reduce the problem is inspection, frequent inspection, which can be costly, but at least you can catch the bad boys. Okay, the most likely events, candidates for events. Okay, incidents that occur during winter months. Why?
Salt.
Sorry? Salt and water, melting ice. Yep. Okay. No data provided for these years, but salt is another problem. Okay, so now you can buy not salt, but another material to melt the ice. Okay, which also has a factor in reducing the number of events. Okay.
Would that be at the city level or putting it on the road? A lot of these manholes might be.
They are on the road or on the sidewalk or anywhere else. Can be anywhere.
The landowner.
The land, yeah, yes, yeah. But you go to Home Depot and you can buy non-salt ice melter compound. Okay. So I don't think there is a complete answer, but there are many indicators, many suggestions as to how to deal with it, how to reduce it, how to eliminate or minimize events. But just like with anything else, you build bridges and the bridges collapse for some reason, either design fault or changes in water level in the bridge across the river. So no matter what you do, something will go wrong. What we're trying to do is minimize risk. Minimize risk. And what's the definition of risk?
What was the question?
What is the definition? How would you define risk? And IEC, International Technical Commission, has a very brief definition, very short definition: absence of hazard. And hazard is defined in another way, so there's a whole sequence of definitions, but basically it's absence of a hazard, absence of danger. Okay, so to minimize risk, you can do all kinds of things. Open up your research, open up your mind, and think of other things, which we try to do by considering many approaches. Okay, most explosions are on 120-volt systems. Okay, so in that case, forget transformer volts, because transformer volts contain transformers which transform voltage from, let's say, 25 kV to maybe 1,000 kV. Sorry, 1,000 volts. But most events are in the 120-volt system. Why? Because that's the largest number of structures, and insulation is not very, very thin, not very, very thick. Okay. So beefing up insulation, that may be one reason that there's a smaller number of events in Europe.
So in Europe, it's
Started at 220.
Yeah, yes, but because of that, the insulation is thicker and maybe over-designed. Yeah. Okay, we looked at the weather conditions, and we statistically, major accidents 78% occur in 120 volts. Nearly 47% occurred during clear weather at the time of the incident. The weather was clear at the time of the incident. There could have been rain or snow or salt before the incident, but it takes time to degrade the insulation. Okay. Next highest weather condition is 25% is thaw, followed by freeze. So salt, ice and salt may be a main factor. Smokers, okay, the insulation was deteriorated. Maybe there was some arcing, sparking, and but not enough gases were evolved. Okay. Now with 120 volts, can you sustain an arc? Yes, we can. We did for 20 minutes. It took some doing, but we were able to sustain an arc for 20 minutes. Okay, but the arc is not continuous in an arc world. You touch it, you move it, touch it, and the distance is very, very small. Okay, and it's acetylene most of the time. Yes,
Electric.
electric. Okay,
You said it took some effort to try to get that arc to sustain itself.
yeah. We took cables, or
But with
very unlikely. because it took a lot of work to create the arc and maintain it. What we had to do, we had to take two cables at 120 volts, very close to each other, crushed carbon, and covered everything with crushed carbon mixed the Vaseline, covered with oil to retain the heat. And that would arc for about,
Okay.
yeah. And that's another story. We were asked to do that at a utility, and you came to that's the test site, and there is a substation, a cable from the substation, or two cables from the substation on some wooden posts to the test area, and we created an arc, and we see the insulation on the cables melting. The manager is yelling, "Turn the power off, turn the power off." They did not install breakers between the substation and the test area. So they had to call the operator, explain what happened, and it took about 15 minutes after the arc started. And the insulation melted off the cables, and they didn't expect it. They didn't think of it. Why should they? They didn't believe us when we said that we could maintain the arc for 20 minutes. So
I can see you maintaining an arc at 480. That's not a problem. Because that just it just won't extinguish. But at 120 or so, I would say it's definitely highly unlikely that you're gonna get that in a real world.
yeah, we did. That's why nobody believed us. And that's why they didn't even.
Well, don't forget. Cables that will fail. The insulation is gone. Your insulation is overheating, is burning.
Yeah.
It's literally burning, and that's going to help conduct the current
Right, carbon.
and
Yeah.
carbon and maintain the arc. I personally witnessed this. I know a few people here that have worked in Manhattan. I saw two manhole explosions. Well, actually, it was one explosion, rectangular covers. They
Yep.
blew, it had to be 20 feet in.
Yep.
It's.
And they were vented covered.
The miracle, nobody was killed or injured. That fall cleared right away. There was no. This other incident, walking around lunchtime, it was on 44th Street. And it was in the middle of the street. This was what you call a smoker. All of a sudden, this thing started to arc and spark and spit, and it just kept going and going and going. And the fire department showed up. They called the utility company. All the fire department could do was just cordon off the area. They said, we gotta wait for Con Edison to come to shut the power down. And this thing kept spinning, burning and arcing. It was unbelievable the amount of power and energy that.
And the fire department is not going to pour water on.
Yeah.
Yeah. When was that?
And both events were in the winter time, with
Yep.
salt, ice.
Mhm.
Strangely enough, Boston Edison did testing at one point in time when I worked there.
Mhm.
Where they proved to the fire department that you can go up and put a fire hose in the ball with an arcing ball.
Mhm.
I don't know if you know Tom Zazelak.
I know Tom Zazelak.
So Tom was my supervisor at that point in time, and he basically created an arcing fall in a bucket of water. And then put his hand in the
Yep.
water. It was an arcing fall, and that was 8 kV to ground.
Yeah.
So he asked me if I wanted to do it. I said no.
No, he was
That
both brave and very knowledgeable.
Yeah,
Still
very,
is.
very smart
Yeah.
man.
I was invited to another demonstration, how to extinguish arcing on an insulator. And again, they took a hose. The fire department was there, but they wouldn't touch it. But they took a hose with a nozzle that breaks up
Right.
the stream and extinguished the fire.
Yeah.
So all kinds of interesting things. Okay, and here is the standard, IEEE standard 2417. The title actually is a guide for early detection, mitigation, preventive measures, and response to smoke, fire, and explosions in underground electrical structures. Okay, and the abstract, you can read the abstract, the scope and purpose and so on. And it is available, you have to pay, of course, for IEEE standards. And that was published in 2022, so not long ago. It took a while to develop that standard. And they refer to most of the tests that we did. And the facility was in Lenox, was finished in 1994. So you can imagine how long it takes to get answers to something that we don't understand. So as I mentioned, this has nothing to do with electronics, nothing to do with the live working, and nothing to do with power engineering. And I'm not sure why you convinced me to do that.
I thought it was intriguing.
Yeah.
It's one of those things there's not a lot of information
Yeah.
available.
And the other topic that I suggested, what was it?
I think it's like three-phase measurement.
Measurements of electrical magnetic fields.
Right.
Yeah. Because there's a lot of panic about electrical magnetic fields. Okay. Well, you have to understand what it is. And calculating the electric field and magnetic field, the electric field is a little bit easier, but magnetic field calculations are quite complicated. And last week, I was lecturing to linemen and engineers on live line maintenance. And I said that they were talking about corona. And I said, corona can appear on the conductor. Yes. It can appear on the ground. How can it appear on the ground? Is 0 volts. How could there be corona? Well, I said, okay. You see that conductor up there, 500 kV, divided by 3 and so on. So that's a high voltage. On the ground is 0. How does the voltage get from, let's say, 300 kV to 0? There must be some way to decrease.
Gradient.
Pardon?
The gradient, right?
The gradient. Nobody understands the gradient. Very few people understand the gradient. It's a gradient.
Another example. So we were at this field location by the railroad, and we parked a truck pretty much underneath the
Bucket truck.
high tension lines. No, it was a regular truck.
Oh.
But the lines were pretty low at this.
Okay.
So we were planning our work, and one of the guys, he leaned up against the truck like this.
I got that. Yep.
Did it again, Oh. And we took a voltmeter, very sensitive, back in those days was a Simpson 260.
Okay.
Beautiful instruments. All we had to do was take the meter lead and hold it up in the air and hold the other one down here, and we got a deflection.
Yep.
So I had to explain to them, you got the voltage gradient, you go from 150,000 to 0 over that distance, and that's why he was getting shocked when he touched the truck.
Yeah. Voltage is a derived quantity. The basic quantity is electric field, gradient. Actually, the basic quantity is displacement vector, which is the electric constant times electric field. Okay, and people don't understand that. So voltage is zero on the ground. It's safe. So I showed them pictures of leaves burned on a tree, or a helicopter hovering above ground with corona on the blades.
Some law.
Yeah. Yeah.
Like, some point going up from ground, you're gonna have voltage.
You have voltage.
Hurts
We
you,
had
tickle you.
at EPRI, we had a electrostatic voltmeter. There are only two devices that measure electric field or voltage. Okay, electrostatic voltmeter and oscilloscope. Okay, the horizontal, the old oscilloscopes, hypotronics, and all the big oscilloscopes with cathode ray tubes. The horizontal sweep is provided by internally, but the vertical is the voltage, okay, or potential. And we had electrostatic voltmeter rated for 100,000 volts, big monster. And something went wrong, so I had to take it apart. What's inside? One plate and one plate movable. And the electric field moves it, and that indicates the voltage. Yeah. That's how we try to measure presence of corona on a conductor. Two pieces of aluminum. And when they require the same positive charge or negative charge, it's straight one. Okay, let's see.
We got a question. I didn't see any accelerometers on the manhole covers. Did just the pressure inside?
Pressure
tell
and
you
temperature.
what's
That's right.
happening?
Pressure, temperature versus time, and of course distance. So we could calculate, estimate acceleration, but we maybe they're doing it now. I don't know. I haven't been there in 15 years, but we did not. We couldn't afford it. They're expensive, and then somehow you would have to. You install the accelerometer, somehow you would have to retrieve the information. Okay, that's not very easy. Versus time. Yeah.
So along the lines.
Yeah.
Okay, that's it. So I will try to show you some videos, if I can, because I wasn't able to do that. But here is one that's inside high speed.
So what are those sides in the middle? What's those flame
Okay,
areas?
let's try it again, and I will try to freeze it.
Yeah,
Okay.
see
On the left side, you can see the wall. On the right side, you can see the wall. Those boxes sticking out are the boxes containing temperature and pressure sensors. Okay, and
Is it like a reflection?
it's not a reflection, it's the pressure and the burning gas bouncing off.
Okay.
the wall. So it's not an optical reflection. It's not, no, this doesn't have volume. Yeah, I'll try. Try to find one. Okay. That's high speed. External on camera. So we could estimate speed from that. Yeah. That's inside. Inside, there it is. It's developing, and the covers is starting to move.
I think you had a
Okay.
slide on this. What was the recorded PSI that you, yeah,
Pardon?
what was the recorded PSI?
I don't remember. I have some in these slides. I have some values.
Is it, you said it looked at like a 13,000
Yeah.
pound slab, so.
But it's not constant PSI. It's peak. It's somewhere here. I don't remember. The peak pressure we can get from the records. Like for example, here, this is pressure and
See that like one impulse, I guess that.
and PSI. This is 0. This is minus 100 PSI. This is this peak. This peak is around 10 PSI. This peak is about and that's temperature, 1,000 degrees Celsius.
So it's not- yeah, so-
Yes, this is measured by that one sensor or another sensor. Yeah. This is not on the cover. But the calculations performed by the professor from Georgia Tech matched the curve quite well. And he was able to estimate together with us what the peak was, what the pressure was on the sides. So if the calculations provide about the same pressure on the sides at the point of measurement, then you sort of assume or claim that the pressure on the cover can be estimated. Okay, here this is 400 PSA. PSI, I think. This is the pounds per area. Okay. This is non-wanted. You may be able to find the reports, EPRI reports. Some of those reports are available to the public. Some you have to pay for. Okay, I did not look for those reports, and I just found a lot of this on the internet. And the standard probably has a lot of information. And then again, you have to pay for the standard. Okay, let me see if I can. Okay, this one. That's the entire roof slab. The cover is still on. It was held by the restraining system. But the roof slab lifted, and I was about 15 feet from that. But I was on the other side of the transformer, so I was protected.
No, that's a problem.
That is the swivel cover with the vents and hooks. Yeah. Not this one. not this one. We mounted the roof above it, above the event, on another one.
I know, David Stabler, at one point in time, wanted to really increase the, concentration a lot.
Yeah.
And to see.
It was about 10% by volume of the mixture.
Are these systems sometimes connected to the sewer system?
Sewer systems, sewer systems and water pressure, flooding. But flooding, somebody, and it wasn't Stadler, but okay, here is the vented cover with a much lower concentration. No, that's not water, that's gas. Oh, the water bottles, those are sensors. Those are sensors. Yeah, we wanted to see what the pressure would be, or whether the entire roof would vibrate. And these bottles fell over. Yeah. High-speed video. Yep. This one is blown away because the cover has openings, a sort of zigzag edge, and it just blew those away. Okay. This is interesting because it has both high speed and low speed. That's low speed, that's high speed. Ignition, reaches the cover, reaches the roof, and the cover starts flying. Not restrained. And with those gases, mixture of gases, acetylene burns very slowly. So you actually get a double whammy. Carbon monoxide, ethylene burn very quickly, so you get a kick, and then another acetylene takes over and gives you another boost, depending on the concentration. And now the cover is slowly. Now it's still not settling in. That one, if I don't remember, I'd have to look. I don't have the results. I don't have the report. But that one probably went 15 feet. That's why we put the roof of the tent about 30 feet up. And in some cases, it actually either melted the hole in the roof or punctured right through it.
You said some pounds, so on that pounds shooting through it.
Yeah, nothing will stop it. Yeah.
The 32 inches around 240.
Yeah, that's cast iron. Now, plastic covers are lighter, but they start ejecting sooner on the pressure curve.
So at one point, I'd speculate that Con Ed was welding manhole covers down for.
That's the worst thing you can do.
Did they go and they cut all those welds after finding this, or?
That's the worst thing you can do. You have to relieve the pressure. This covered, actually, maybe you saw in the roof a hole. Actually, we repaired it, and the cover did not puncture through the roof. It came down.
Eversource Boston has replaced, I think, 66% of their existing manhole covers with an energy release result.
Yeah.
And they're continuing to go until they get 100%.
Yeah.
They haven't started that process down here in Connecticut yet.
Not yet, no. No, I left April at that time already. But Zazarok visited us, and I visited him a few times too. Yeah.
Change them all. Some,
Great.
My guess is no. But again, they bought the amount of.
I'm gonna knock this up on.
There was a question in the chat, or a comment. He says that Neil says it seems counterintuitive that it would take on the order of 200 milliseconds for the flame front to propagate from the igniter to the cover location.
And that's what we said.
It takes.
It takes time.
that long.
It takes that long, but also with a mixture of gases, you get different fronts, and depending on the size of the inside volume, it bounces off the walls. The two walls are close, the other two walls are far away. Okay. Cancel.
Explosions local to gas mixture is, or does it propagate to the rest of the trench? Just
It does not transfer from one to another. And we even had fans trying to suck in. No, it doesn't. It's just too fast.
Thank you very much for the
You're
nice
welcome.
presentation.
Yeah, thank you. And how do I get rid of this again? Okay. I'm trying to start this one, but it doesn't work for some reason. It's not helping.
Yeah, that was good.
Well, we do monitoring as well. Number of panels, just to see if they can identify any. Potential overheating of cables that would generate the gases, so. But it's not that one,
It's not,
and it's expensive.
maybe it should be.
It's expensive.
It is. Yeah. Monitoring temperature on every piece of cable when you have 6, 7, 10.
Well, I think what they're doing is they're using cameras.
Yeah.
Infrared cameras get that, they can just focus in manhole as well as other types of monitors, gas monitors, everything else.
Not on every manhole, but
Not
on
like
structure.
I don't know how they select the man.
Not like this. No. In Manhattan, I know that they look at the system and position cameras or sensors in selected locations, either based on historical information or when there is likely, a vibration, heavy trucks, salt.
Yeah.
Yeah. Yeah.
Potentially.
Tab block locked, 6% by this. Yeah. That's a nice one.
I can hear you.
Everybody was excited. Yep. And we had to explain, in this case, we had to explain why was the entire structure damaged. This is the research. If we knew what would happen, we would have to do it. %6% UL mixture is the four gases. The lock well held, but cover lifted 2 inches, I think it said. So that's it.
Yeah, well, very good. Thank you
You're
again.
welcome.